I just wanted to do a little epilogue or post-mortem, if you will, on Brian's great presentation on this case study of the Wrangler from hell. First of all, I wanted to reiterate what he said, that this particular engine, this 4-liter cast iron head and block pushrod motor, is an extremely reliable design, has served well for many, many years, and we're not suggesting there's anything wrong with the design here at all. This is strictly a problem with the vehicle. And to just clue you in what the actual solution was, the solution was the replacement of the lifters for the number 6 cylinder, specifically the exhaust lifter. And in this photo we can see the exhaust rocker here, the intake rocker. And here's the shim we put under the intake, and there's a thicker shim here under the exhaust. I'll tell you exactly how that happened. We came by putting a thicker shim here. The first time we did this, we of course removed the rockers and the rocker stands, and found that we found appropriate washer thickness to put underneath there to generate some valve lash. And theoretically, of course, when you release the pressure on these push rods, the lifters should fully extend. And so we did that, and we had good clearance on both valves for cylinder number 6. And it was interesting when we put the valve cover back on, restarted the engine, and got it back into its failure scenario, it started missing again. And we're going, no, wait a minute. We're sure it's a lifter problem. How could this be? So we quickly pull the valve cover back off and notice that the lash on the exhaust valve is now gone, whereas the lash on the intake valve here was still present. So we got a thicker washer to put underneath there to make sure we had plenty of clearance. And now, of course, there's so much that we can hear it tapping, right? But when we did that, the problem was gone. So that's how we know for a fact that it was an exhaust valve lifter that was causing the problem. And we were able to report that to the technician working on the vehicle, and it went back there, and they changed both of the lifters for this cylinder just for good measure. And that solved the problem, and the vehicle is now on the road and belongs to a happy customer. So here's our theory on how the exhaust valve lifter was actually causing this problem. Now, there's not enough hydraulic pressure in the oiling system to actually open the valve with hydraulic pressure through the lifter. So there has to be something else occurring, which is causing the clearances to change. So when the vehicle first starts up, it does not miss. As soon as it begins to warm up, it does, and then it goes away when it's fully warm, about the time the thermostat opens. So here's our theory. Our theory is that when you first start it up and it's cold, that exhaust valve lifter cannot collapse. It can only extend, it cannot retract. Therefore, as the exhaust valve begins to heat up, it's going to be the fastest thing to get hot. Stem gets a little longer. Lifter doesn't take up for the additional expansion, and the valve is held just very, very slightly off its seat. And at some point, when other things begin to expand, the oil gets thinner, the lifter changes temperature. It's all temperature related, and it just goes away. And anyway, that's our theory for exactly how the lifter caused the problem. We'd also like to acknowledge All Data for their information database and some of the information that was presented here from the All Data system. This system is the most complete source of factory information available, bar none. So follow the link here and do check that out. It is the best source of factory information, short of going directly to the factory sources and subscribing to each and individual manufacturer's factory information website. You can't get more accurate than factory information. A lot of the other systems do have a lot of errors and lack of information, partial information, incorrect information. Of course, there's mistakes in everything, and even factory information has mistakes, but it doesn't get any better than that. So if you're like I am, you make enough mistakes on your own, and you don't need any help from your information system, get the ALLDATA. Save yourself a headache and a lot of money in running around in circles and wasted time. But moving on this particular example, this vehicle being a 2003, only 23,000 miles on it, 25,000 miles on it, and it's 6 years old, right? And it has been this way since it came off the showroom floor. There's a long service history up and down the West Coast, various dealerships, various owners. No one in 6 years had solved this problem, although many had tried very diligently, particularly the technician who passed this on to us. When we got involved in it, we thought it was interesting, and we volunteered to look at it. All they had to do is bring it by the shop, leave it here for as long as we wanted it, and come get it when we were done. And we found it an interesting diversion and a very good way to demonstrate some scope diagnostics. So the question is, why? Why was no one able to solve this problem in all that time? I mean, we're not any smarter or more skilled than the technicians that had already worked on this vehicle. We just had better equipment. What it took during this running compression test is to actually capture enough time on the screen to see this very gradual trend. And as you can see, and as previously mentioned in Brian's presentation, there's 8 minutes and 20 seconds of capture time on this screen. And when we actually measure with the rulers here, let's measure the trough here when the compression fell, and then when it recovered at the end, there's only like 24-pound difference. That's not a lot, but it created a lot of turbulence in the combustion chamber, disrupted the spark behavior, killed the cylinder, and was responsible for this problem. And this is the money shot. I mean, this is our first one we actually saw where we had the whole event on the screen at one time. And the difference is, over here, we can see the starting event and the decrease in compression. Of course, this is partially due to changes in RPM and IAC and this sort of thing. We weren't really sure if this was normal or not at this particular time. But when it did settle down and idle after about 3 minutes, 4 minutes or so, and we're missing on the cylinder, and then all of a sudden, the compression goes up with no change in throttle, virtually no change in engine speed. That set off all kinds of alarm bells because that's just not right. Okay, that just can't happen. So there's obviously, this proves that there's an actual problem in the combustion chamber. It's not like running compression tests hadn't already been done to this vehicle using a mechanical gauge. Okay, but think about how much time this is. I mean, who's going to stand there watching a mechanical gauge for 8 minutes and expect to see a gradual change in a fluttering needle of only 25 pounds or so in this particular capture? I mean, who's really going to be even looking for that, much less be able to see it? It's like looking at scan data over graph or scan data in analog format. You see a bunch of numbers switching around and, you can see it, but, over a long period of time, you don't really register that trend. And that's why this capture here was so very powerful, because it showed us precisely what was wrong and exactly how it was happening. The only thing we didn't really know is precisely which lifter it was. We were pretty sure it was a lifter, and that's what the whole washer thing was all about, to prove that theory.